For the key idea behind the set theory, when we consider an image, how we are going to represent an image with respect to the sets. So, if we consider foreground pixels, those will be denoting your members of a set, and the background pixels of an image, those will be you are considering as a non-members of a set. Morphological operations that we are going to perform. So these are nothing but the set operations on the image pixels. So this is the basic concept and how the set theory we are going to apply. So let us see how the image is represented as a set. So consider an binary image which is defined on a coordinate grid of all the positive values, right? So z square is the common denotation of this. So if A is represented as an object, let us say white pixels. Okay, so I have an image which has certain object on it and which has a white colored pixels. So this set is represented with A is equals to, it is a pair of xy such that it belongs to z square, and here I of xy, that is intensity of the pixel at xy position, is equals to 1. So this is nothing but I have represented the object of the image which are having white color. Okay, so here I of x comma y is equals to 1. It is nothing but it consists of a pixel, or it denotes a pixel which belongs to the object, so that is the foreground of the image, right, which is appearing more prominently. Then I of x comma y is equals to 0. If it is, then the pixel belongs to the background. So this is my simple consideration. Let us consider I am having one 5 by 5 binary image. Okay, so here few pixels are having value 0, few pixels are having value 1, and so on. So here if I denote this image in the form of set, so how I am going to represent it, that with this set definition. So this is my set definition to denote the object of white pixels. So where I have denoted the pixel value, if x comma y pair, if it is having 1, then I will write its pair, right? So here this pixel, look at my cursor point. So this pixel is having value 1, this pixel is having value 1, this is 1, this is 1, and this is 1. So the set definition for this kind of image where rest of the rest of the image pixels are having value 0, it will be denoted with a is equals to, see, this is the first row and third column, right? So 1 comma 3 I can write that as a 1 pair. So then this 1 comma 3, then another thing, that is 2 comma 2. So this is also having a value 1, so this will be 2 comma 2. Then this pixel, this is 2 comma 3, right? Then this pixel 2 comma 4, then this pixel 3 comma 3. So this is the set definition for this kind of image, which is of size 5 by 5 and it is binary. So whichever pixels are having value 1, only those pixel pairs I am going to write, right? So uh, what we have done here, instead of thinking the entire picture, now we are only looking at the set of coordinates whenever we are going to represent an image in the form of a set. Okay, we are not bothered about rest of the pixel positions. So this is nothing but a simple representation of an binary image with set. Let us see about what are the fundamental set operations for images. So we need to understand certain basic set theory when we need to perform any image manipulation. So we will focus on union operation, intersection operation, complement operation, and the difference operation. So in terms of set operations that are performed on the images, the union operation, it is, as you know that you usually you have two sets with you, let us say A and B. So union is denoted with A union B. So this is the symbol, you know that. So union operation, what it does, it combines two sets, right? So in terms of images, what union operation will do, it will simply add together all foreground pixels of the two images. Okay, for example, if suppose A is a circle, A denotes a particular circular object inside, and let us say B denotes a square, then the union gives the combined shape of these two images, right? Understood? Because union, what it does, it simply combines two sets together. So now if I'm having two images together, so union of these two images will be the combination of these two images, right? Then intersection operation on images, it keeps only the pixels that are present in both sets. So if suppose A is a circle denoting one image and B is a square image, B is an image which denotes the square, then the intersection of these two images is nothing but the overlapping region of circle and square, right? So this will be giving you the intersection. The complement operation of the images denoted with a complement, let us say. So what it does, it simply swaps the foreground and the background. Okay, for example, after swapping, white pixels will become a black and black pixels will become a white in terms of binary images, right? So this is what the complement of uh, a binary image will be. If I need to perform the difference of images, difference of two images, so let us say denoted with A minus B. So here what difference operation will do, it will simply keep the pixels in A that are not in B. So A minus B is nothing but this difference operator will keep the pixels of image A that are not in B. Okay, for example, if A is a square and B is a, let us say, some smaller circle inside A, right? So here the result will be the square with a hole because B is subtracted, right? So we are going to keep the pixels of A, but we are going to discard the pixels that are not in B. So these are the basic operations that already allow us to manipulate the images in a mathematical way. We have few more operations, that is translation and reflection of the images. So the translation is nothing but translation denotes moving of the object set A by some particular vector z. So it's denoted with az is equals to a plus z such that A belongs to a set A. For example, if suppose A is a pixel at, let us say, 2 comma 3 and we translate it by 1 comma 2. So the new pixel will be simply the addition of these two. So original object plus the kind of move that you are allowing, right? So we are going to simply move this pixel by 1 comma 2. So this is a kind of translation we are going to perform. So this is called as a positional translation or the positional movement of a particular pixel. Okay, so the output will be this 2 plus 1, that is 3, and this 3 plus 2, that is 5. So after moving the object of set A by 1 comma 2 on a particular pixel position 2 comma 3, the translation uh, result will give you the new pixel at 3 comma 5. Okay, in terms of reflection operation, so reflection is nothing but flipping the set B about the origin. So it's nothing but you are simply let us say you have what you can say, how you perform the flip, right? You perform the image flip by either side, either right side or left side or upside or downside, right? So this is nothing but the reflection. So flipping of a set B contents about the origin. So this is denoted with B reflection, B cap is equals to minus B such that B belongs to set B. So for example, let us say I am having B is equals to 0 comma 1 and 1 comma 0. Then B cap, it will become 0 minus 1 and minus 1 0. Okay, right? So positive becomes negative and negative becomes positive. Likewise, we are simply allowing a kind of a flip on a position, right? So these two operations, the translation and reflection, these are very important because the morphological operations, they always require reflection and translation of the structuring elements most of the times. Okay, so remember these 2 points. Next point we will consider is the dilation. So dilation operation is nothing but we are trying to grow or expand the objects of the binary image. So consider, suppose for example you have a balloon and if you inflate it, so what will happen? The balloon will grow outward, right? So in the same way, the dilation makes the shapes of the image quite thicker. If you perform the dilation of the image, if you perform the dilation on the image, so whatever contents of the image are, they becomes thicker. Okay? So dilation is often used when objects are broken or they have certain small gaps and that require a filling. I need to fill those gaps. Okay, so whenever such a scenario is there, we are going to perform the dilation. This is because the dilation will make the objects thicker. The mathematical definition of the dilation, when we have, let us say, a certain set A which has a set of foreground pixels which denotes the objects and B is the structuring element, then the dilation of A by B, it is defined as A XOR B is denoted with, it is the symbol to denote the dilation operation. So we use the XOR. So A XOR B is equals to, it is a set of elements Z such that Z belongs to B cap. Okay, we have seen what is the B cap. Yes, so we are performing the reflection, right? So after performing reflection, whatever your results are, those are the set elements you will have. So those set elements will be denoted with Z, let us say. Okay, and this intersection of those elements is not equal to null. So this is the mathematical definition of the dilation. So here B cap is nothing but the reflection of the structuring elements of B set. B cap of Z, it is the translation that you are performing on the structuring element of B cap after reflection. Okay, so this is nothing but you are going to provide certain amount of Z over here. So this is denoted with a certain vector. So this translation factor denotes the vector Z. Okay, then not empty, that means at least one overlap should exist. That's why we are considering, so that only then the dilation occurs, otherwise it won't occur. So interpretation of this is nothing but what I can say is, let us say place a structuring element with every possible location of the image. So if at least one structuring element pixel, if it overlaps with the another object pixel, then mark that location in the output image as a foreground. Okay, so only overlapped regions of structuring element with the pixel positions. only those overlaps are marked as the output image as a foreground. I hope this is understood to you. We will see the solved examples also, then more concepts will be clear. So consider, suppose I am having this image. Okay, let us say I am having this input binary image A denoted with certain zeros and ones in it. Okay, so here uh, what we can say is this represents as if these objects, wherever the pixels are having one. So if I just visualize it, it appears as if it is a symbol of plus, right? So this image denotes an object which is having a plus symbol shape, right? So now let us choose one 3 by 3 square, because this plus symbol, if I observe, this falls in first three columns, right? So that's why I'm choosing a square 3 by 3, which is having all pixel values as ones. So this is my assumed structured element. Okay, so structured element is nothing but depending on my image contents, I am simply selecting any vector. So this is my structuring element. So when we perform dilation on this image by this structuring element, so here each one pixel in the input image, it expands to outward size by 1 pixel in all direction, because this is my square that I have chosen. So so the result of this will be the plus shape, it becomes quite thicker. Okay, so this is nothing but what will happen over here. So if I chose this, if I place this SC is nothing but my structuring element. Okay, this structuring element, I need to place it over here on this input image. So wherever overlaps are there, those overlaps will be marked in the output image as a foreground. Okay, so this 0 overlapped with 1, so it becomes 1. This 0 overlapped with 1, this becomes 1. This 1 overlapped with 1, this becomes 1, and so on. Okay, so everywhere I need to put it. Fine. So in this way, the output after dilation I get as the entire first row is having all ones, second row is having all ones, third row is also having all ones, and fourth row is also having all ones. Okay, and in the last row only this pixel will be having a value as 1. So here you can just observe how the objects has grown to a larger size, right? Okay, just consider one more thing. Suppose I am given one set object denoted with A. So A is equals to, let us say, 0 0 comma 1 0 comma 0 1. So if you draw the image for this, so it is nothing but the pixels at location 0 0 is having value 1, the pixel at location 1 0 is having value 1, then the pixel at location 0 1 is having a value 1. So if you draw this image for this, so it is nothing but one L-shaped object it is. Okay, you can just take a pen and paper and you can just draw a matrix for it, and you can just observe it is simply representing one L shape. And let us say you choose a structuring element denoted with B, which is equals to pixel positions at 0 0 is having value 1, pixel positions at a place 1 comma 0 is having a value 1. So it is nothing but simply a horizontal line of 2 pixels. So this is my structuring element. Structuring elements are usually smaller than your input image. Then what is the first step to perform the dilation? We first reflect B. We perform reflection operation on the structuring element. So if I perform reflection on B, then my B cap, it is equals to this 0 0 origin remains as it is, right? Because origin को अगर हम flip भी करेंगे तो it will, the position will remain same, right? So it will have 0 0. For this 1 comma 0, now it will become minus 1 and 0 because we are performing this flip on it. Next step, we perform the translation and then we check for the overlap. So here, place this B on each position on this grid of L shape. So here, whatever part it touches to the object A, include that location in the result. So here, if I perform A overlapped with B, so this 0 0 overlapped with this, so it will what this 0 0 comma 1 0 comma 0 1 overlapped with 0 0 minus 1 0. So what you will get, the results will be at this 0 0, then this 1 0, right? Then I get 2 comma 0, then 0 comma 1 and 1 comma 1. So here the L shape has expanded to the sideways, making it more thicker. Okay, so here uh, you should be able to perform the XOR operation between the two sets, right? So that is more important. So you just identify just how XOR is performed between the set elements. Okay, they are done one by one, right? So every element of set A is XORed with every element of set B, and you will get the result. Okay, these are certain properties of dilation. So expanding property, dilation always makes the objects bigger. So that is the basic thing, or we can say that the basic property of the dilation. So it is called as a expanding property. So A is a subset of A XOR with B. Then commutative property, it is like when I perform the XOR between two sets or the two images, or one image or even your structuring element. So that XOR operations order, it doesn't matter. So A XOR with B or B XOR with A, you will always get the same result. Associativity property, so A XOR with B, you first do this XOR and then you XOR the result with C. So this will be equal to the XOR of B with C and XOR of A with that result. It will remain the same. There are certain applications of dilations. These are the applications. So if I need to fill certain objects, so let us say the objects are having certain holes in it or some empty regions in it. So if I want to fill those regions, so I can perform the dilation. So filling small holes in the objects is one of the application. Then if I have let us say the structures, suppose I am having, there are certain broken lines in the object, on the object boundary, let us say. So whenever I need to connect those broken boundaries or the broken lines, I need to perform the dilation on it. Then if suppose I need to emphasize on the main shapes, I want to expand those shapes, I want to expand particular shapes of the image, then I will perform the dilation. If I need to perform boundary extraction of the images also, then also I can use the dilation operation. Okay. So that's all about the dilation. Next morphological operation, that is erosion. So erosion, it means shrinking or thinning of the objects in the binary image. We have seen the expansion that is performed with the dilation, right? And erosion is an operation whenever I need to shrink the images, or we need to thin the objects, or we need to let us say, it's nothing but I'm simply compressing it, right? I'm simply compressing the objects of the binary image, so I will perform the erosion. So suppose I'm let us say, a very simple example, suppose I'm having a soap bar. So what happens when we use that soap? So regular use of the soap, what it does, it slowly warms away from the edges, so it gets thinner, right? So the erosion is performed in the similar way. So erosion makes the shapes in the image thinner. It is useful when the objects are too thick, or even when the objects are having certain small unwanted noise, and that must be removed. So uh, uh, in such cases I will perform the erosion. The mathematical definition of this is, let us say, suppose A is the set of foreground pixels that denotes the object, and B is the structuring element. Then erosion on set A with respect to the structure B, it is given with this symbol. Okay. This is the standard symbol for denoting the erosion. It consists of uh, the pixels, what we can say, it consists of the elements z such that it belongs to the translation of the structuring element b, and which is the subset of the set A, such that this bz, the bz structuring element, it completely fits inside the A object. So here how we can just achieve this is, let us say, suppose we are placing the structuring element on every possible pixel location of the input image. Then after performing this, we only mark the output pixels wherever the structuring element is completely inside of the object. Okay. So those, if such cases are formed, then only we will mark with the output. So let us consider, suppose this is my input binary image where all the pixels are having the value as 1. So this is like, I can assume this is a filled square. Okay, so this is the complete square which is having the entirely filled, right? ठीक है ना? Are you able to imagine this kind of image? एक complete filled square है, it's only the square thing, right? So now suppose I choose a structuring element with a square that is 3 by 3 size. So when we perform the erosion, only the pixels where the 3 by 3 structuring element completely fits inside the squares, these are kept. So the result will, it will simply shrink to the 3 by 3 size. So this is like, I will simply put this 3 by 3 square of all ones, right? So I will get the center pixels after filling. Okay, but if I chose a 4 by 4 square, 4 by 4 size structuring element, then I will get these 4 rows, because this is completely filled over here. Okay. So rest of the pixels, wherever it is not fitted properly, or wherever it is not filled, right? Those all excluded pixels I can consider to mark with the 0. Okay. So this is like, this is my output after performing the erosion. So only the central pixel will have the values as ones, and rest of the pixels, these will be having the values as 0. So this is a kind of shrinking that we have performed on this input 5 by 5 image. Okay. You understood how the erosion works? So what you can observe is, after erosion I can see that this image object becomes smaller in appearance. Okay, so erosion makes the objects to shrink. They will make objects to appear more smaller. So this is the property of erosion. For dilation, we are going to expand the objects, and for erosion, we are going to shrink the objects. Okay, understood? Okay. In terms of set theory, how erosion is done, I will explain. This is what how it works on the direct images. You have the image, you have the structuring element, you place the structuring element over the input image. Wherever the structuring element fits properly inside the square, then we are going to keep it. Now let us deal with uh, the erosion operation when they are represented with sets. So suppose I am having the object set A denoted with these pixel positions. So this is nothing but if you draw it, 0 0 is having value 1, 1 0 is having value 1, 2 0 is having value 1, 0 1 is having value 1, pixel at 1 1 is having value 1, 2 1 is having value 1, 0 2 is having value 1, 1 2 is having value 1, 2 2 is having value 1. So this is nothing but, let us say, my 3 by 3 square. Okay, where this 3 by 3 square matrix is having all values as ones. And let us say I'm having a structuring element which is having two pixel positions, 0 0 comma 1 comma 0. So 0 0 is having value 1 and 1 comma 0 is having value 1. So this is nothing but a horizontal line of 2 pixels. So if we perform erosion on it, so the step 1 that we will require is, as per the mathematical definition, I need to perform the translation. I need to perform the BZ. So BZ is nothing but the translation of the structuring element by a vector Z. So here we simply perform the translation on this structuring element. So what it will be do? It will simply slide the B across the object. Then we check for the fit. Like we place this translated B on the object set A. So what we will get? Yes. So wherever the B is fitted into this 3 by 3 square image, and this is my 2 by 2 size, right? So this will be having this will give you the shrinked object. So completely thinner object I will get, right? So this is nothing but I am having a horizontal line of 2 pixels. So erosion will give me the original square which has been eroded horizontally. So it has become thinner in a horizontal direction. Okay, so this will be my result. You can just draw the set A. You can just use the set A denotation. You can just